let's make the official starting time. Let's make the official starting time 10:40 on next week, and we'll talk. The talk is until 12:30 with a break in the middle. So let me recall the definition from last time. I need a better. גיל, את יכולה להביא כזה טושים?
כן.
So a DV simplicial complex is a simplicial complex with at most V vertices and all degrees are at most D. And so this is אז יש טוש? מולה. אבל לא יראו שחורים. So and so this is these two parameters bound the combinatoric of a simplicial complex, and in the future D will be a constant and V will be the volume. And we would like, given a manifold of volume V and dimension, fixed dimension, we'd like to construct a simplicial complex which is homotopy equivalent to the manifold, and is dV, where D is dependent only on the dimension and V is the volume. And so maybe let's see some consequence of this. So let's try to understand a bit what does it mean. So first, I said last week already that we only give bound on the number of edges on the first skeleton, in a sense, because if you bound the degree, okay, V bound the zero skeleton, the number of vertices, and then the number of edges is at most D times V over 2. But it's also bound the number of two simplex, because in each vertex there are only D neighbors, so there are only D choose 2 possible triangles. So V times D choose 2 divided by 6 will be a bound on the number of two simplexes in such a, and again, so it's linear by V. There is some constant, maybe large, depending on D, but it's linear by V. And then you can bound the number of three simplexes and so on. So all the combinatorics is bounded linearly by V. And this is the parameter that will be large. So here is so two remarks, or two facts. Fact 1. The fundamental group is presented as a small presentation. So let R be a dV simplicial complex, then pi1 of R admits a presentation so that means that you can write pi1 of R as a set of relation and sets of let's say set of generator sigma and set of relation where the size of sigma is bounded by some constant times V, the size of R is also bounded by some constant times V. And also all relation for any W in R, the length of W is at most 3. So without this data, this is much weaker. To find a presentation with linearly many relation and linearly many generators is one thing, but if you also bound the length of the relation, this tree is not so important. If you bound by 10, it's basically the same. But the fact that you can bound the size of the relation without adding too many relation is very effective. And the proof is immediate. So proof of this fact. So let T be a spanning tree for I have this dV simplicial complex R, and I look on its first skeleton. Its first skeleton is a graph. I remember only the vertices and the edges, and I take a spanning tree. So every graph, every connected graph, you can take a spanning tree. It doesn't matter so much which we take. So let's try to draw the simplicial complex. Some of the, I don't know. This is a simplicial complex, and I take a spanning tree. That means I take a vertex and I start to build a tree from it. There are many ways to do it. I'm drawing one. Okay, this is a tree. And now for every edge which is not in the tree, I add a generator. Every edge which is in the first skeleton but not in T defines a generator. So, okay. So I look at pi 1 with respect to this vertex, and then I have this edge. So this defines this generator on the fundamental group. This edge will define this generator of the fundamental group. Every edge, it closes a circle and defines a generator, and you can easily check that this will generate the fundamental group. And then every two simplex defines a relation. So I have this is not a two simplex. So this generator is, but this is a two simplex. Let's actually make the picture a bit more complicated. Suppose we have here another two simplex. And this belong to the spanning tree. And these two simplex, let's say this one is closed. So you see that every two simplex give me the one relation. So for instance, this one will say that this generator is actually equals to 1. It's trivial in fundamental. But this two simplex will say that so this one generator, this is a second, this is a third, so the product of the three of them equals to 1. So it will give me a relation of length 3. So you see that the relation that two simplex gives is either of size 1, 2, or 3. And since the number of edges and the number of two simplices is bounded linearly by V, we get this fact. So this is nice. Another fact. What should I raise? The proof or the?
The question.
Yes.
Who is C?
C is some constant depending on D,
okay.
and let's say C is a constant depending on D. It's a good question. C depend only on D. It's not depending on D. Okay. So another fact is that the number of such of DV simplicial complex is also bounded by, can also be bounded. So fact 2 is that the following: there exists C, again depending on D, I can take the same one, such that the number of all DV simplicial complex is bounded by V to the C. This is a counting exercise. The proof is an exercise. So you need to give a lower bound and a upper. Actually, yeah, maybe it's even okay. The two constant Ci I equals 1, 2, such that this is also bigger than. So it's bounded between two such constants. Maybe you can be more precise here, and maybe it's even asymptotic. Yeah, you can say more. But later, maybe even today, I'll show you the lower bound. Because we will want to construct manifolds. We will show that this construction of manifold in particular will construct simplicial complex. The upper bound is completely elementary. In fact, there is a nice exercise to show that the number of D regular graph with V vertices is about V to the V. And then you can, I mean, it's really, if you think about it 2 minutes, you see that you can bound the number of simplicial complex. It's really a simple exercise, so I leave it. Or you want me to? No, it's really, okay, now recall the conjecture. So last week I formulated the conjecture for a hyperbolic manifold. I want to be a bit more general. So an important definition in this course is a symmetric space. And another important definition is a Hadamard manifold. So let me just give this definition, and later we'll discuss them more systematically. But for now, just the definition. So a symmetric space is a Riemannian manifold, 2M or 2N?
2N.
3N. A Riemannian manifold such that at each point you have a reflection in the point, such that it's a Riemannian manifold, let's say X, such that for every point inside X there exists, or let's say a symmetric space is, let's say, simply connected.
Doesn't it follow from
It follows, except in dimension 1. It's circle, but
no, it does, but then the torus is also
yeah,
it doesn't follow.
Yeah. But okay. A symmetric space is a Riemannian manifold such that for each P there is an isometry. There is an isometry of R, of X, fixed in P. Isometry, let's call it TP. such that TP fix P and reflect geodesic. So every geodesic goes to its inverse, and so you can say that the differential of TP, the differential at P is minus the identity. So in the tangent space, it's actually minus the identity. So this is a symmetric space. There is this Hadamard theorem which says that okay, maybe just example. So the first three examples is Rn, Sn, and Hn. We'll see many more examples, but Rn is the Euclidean space of curvature 0, Sn is the sphere of curvature 1, and Hn is the hyperbolic Lobachevsky space of curvature -1. They're all simply connected, except this one they're contractible, and this is somehow exception because it's flat. This is an exception because it's compact.
This is an exception because it's flat.
And yeah, so a symmetric space admits what is called Hadamard decomposition. So the Hadamard decomposition say that every symmetric space, so this is the Hadamard decomposition. Every symmetric space is a product, is a Riemannian product direct product of irreducible one.
What is Riemannian product?
Riemannian, what is it? It means that the metric. So it's just a product. I mean, a product of Riemannian manifolds, and the distance is just it's like
Pythagoras?
what? Yeah, like Pythagoras. The distance. So on the tangent space, it's like it's just like the L2 direct sum of the tangent space to one and the so it's a Riemannian product of irreducible one, and it's and this decomposition is more or less unique, except in the Euclidean factor. Of course, R2 you can decompose in many ways, but except that, this decomposition is unique.
What is irreducible?
Irreducible means that you cannot decompose it further. So this is irreducible and this is irreducible. R2 is not irreducible. And a symmetric space of non-compact type, X is of non-compact type, this means that if it does not have...
Now I get it. It's a finite product.
What?
It's a finite product.
Yeah, of course. We speak about finite dimensional manifolds.
Okay.
Yeah, we stick to finite dimensional manifolds in this course. So it's of non-compact type if it does not have a Euclidean factor, no compact factor. So I don't want factor like this or like that. Example, H2 cross H3. This is a symmetric space of non-compact type. It's not irreducible. It's a product of two hyperbolic spaces. And I will say much more about it in the future, but there is a nice equivalent between the category of symmetric space and category of semi-simple Lie groups with no compact factor. The isometry group of every symmetric space is a semi-simple Lie group with no compact factor, and every connected semi-simple Lie group with non-compact factor is the identity connected component is the basically the isometric group of some symmetric space. So there is a one-to-one bijection between symmetric space and adjoint semi-simple Lie group with no compact factor. So to study locally symmetric manifold, and one fact is that X, a symmetric space, is of non-compact type. A symmetric space is of non-compact type if and only if the curvature is non-positive. Not if and only if, because let's say a symmetric space with no Euclidean factor. Okay, if it's of non-compact type, then the curvature is non-positive. A symmetric space of non-compact type have non-positive sectional curvature.
What do we define? What?
I don't know.
I'm not defining it now, but this one has curvature, positive curvature, and this one has negative, non-positive curvature. I will say something about curvature. I will define what non-positive curvature if you want. Okay, a locally symmetric space is a manifold such that a locally symmetric space is a locally symmetric space is a manifold which is locally isometric to a symmetric space. Is a, let's say, complete Riemannian manifold locally isometric to a symmetric space. So it means that at any point you have a neighborhood which is isometric to a neighborhood in a symmetric space. And the universal cover of a locally symmetric space is a symmetric space, and the fundamental group acts on the symmetric space by isometries. So more precisely, if we will use this terminology, if X is a symmetric space, an X manifold is a manifold M of the form X mod gamma. An X manifold is a complete Riemannian manifold locally isometric to X.
You say complete now, but you didn't say it before because it followed from the definition, or just because?
No. So an X manifold is of the form always of the form M equals X mod gamma, where gamma is some subgroup of the isometry group of X, which is discrete and tangent free.
For Tal's question, I think the answer is yes. That it follows that if a symmetric space by your definition has to be complete. That's I think.
What do you mean? What is my definition? I require that it's complete.
No, in symmetric space you didn't require it's complete.
A symmetric space has to be complete, yeah. But a locally symmetric space, I mean, you can just take the sphere and remove a point.
Yeah, no, I understand.
Yeah, a symmetric space is always complete. But a locally symmetric space, I want it to be complete, and then its fundamental group act via deck transformation on the universal cover, which is a symmetric space, and it's always of this form. So yeah. But if it's not complete, it's not true. So I restrict to complete when I consider locally symmetric space. Okay, let's now restrict to symmetric spaces, and this is a Lie group. This could be SL2R, SL2C, SL3R, any semi-simple Lie group. It means a symmetric space. For instance, the symmetric space of SL3R, it's some very interesting 5-dimensional space. We will talk about it later. And in a sense, to study X manifold is the same as studying discrete subgroups of this Lie group. So this is, and last week we restrict to the case that we did this overview, only consider hyperbolic space, considering hyperbolic space, and now I want to consider more general, because I want to formulate a conjecture and a theorem, and we're still in the introduction here, so we're still on to proof. But I can consider even more general what is called a Hadamard manifold. So maybe I also define Hadamard manifold.
Can I ask a question?
Yeah.
You wrote that an X manifold is always of the form something mod gamma. Can you say a few words? Why is it an exercise or?
I will say I will discuss more about symmetric space. I'll discuss more. I just want to say the definition. So it's not very difficult, but it's from the theory of covering spaces. So what is Hadamard space? Hadamard space. Hadamard space is a contractible. I mean, you can say simply connected, and it will follow that it's contractible. It's a contractible manifold. Riemannian manifold of sectional curvature of non-positive curvature. For those of you who are familiar with some geometric group theory, Riemannian manifold of non-positive curvature, it's exactly Riemannian manifold which is cut zero. But if you are not familiar with curvature, so in Riemannian manifold you have geodesics. Geodesics are locally minimizing paths. You can define them by solving some differential equation or just by this property. And non-positive curvature, positive curvature is equivalent to the fact that the distance from x cross x to r is convex. It's convex function. It means that if C1 of t and C2 of t are two geodesic, so imagine two geodesics, then the distance of C1 of t to C2 of t is a convex function.
Have a unit speed.
You don't have to require.
No, but the same speed. Or,
yeah. You don't have to require even the same speed. So you can restrict. You can restrict to unit speed, and this will be equivalent to non-positive curvature. But then, if it's non-positive curvature, then you can take them of different speed, and it's also convex. I mean, you can think of two geodesic on the sphere, you see that the distance between them is concave at the beginning. And but in the hyperbolic space, it's convex, or in Rn, it's convex. And this is equivalent to non-positive curvature. So once I said it, I don't need to define curvature. But I can define curvature. But maybe let's not spend time on this at this moment. So this is non-positive curvature, and this is the Hadamard space. And more generally, we speak about symmetric spaces, but we would like to understand many of the things that we'll do will be generalizable to Hadamard spaces, and we would like to do it in this general way. So let me now repeat the conjecture that I said last week. Conjecture. I said that like the motivating question in this course will be, what can we learn about a manifold if we only know to measure one parameter? If we only know the volume, what does it say on the manifold? So yeah. So what restriction does it give? And this conjecture does not it doesn't summarize all what we want to say about the manifold, but a lot of it. If it's not everything can be encoded in this conjecture, but many things. So so let me stay with symmetric space. So let X be let's say an irreducible this is one formulation of the conjecture, symmetric space of non-compact type. For instance, hyperbolic Lobachevsky space of non-compact type, and let's say the dimension of X is not 3. In dimension 3, the story is different. Then there are D and alpha such that any X manifold M is homotopy equivalent and is homotopy to D alpha volume M simplicial complex. Well, this constant depending on X, these two constants. So this is the conjecture, which should be true. You can formulate a similar conjecture in the ring of Hadamard manifold, but I prefer to say it as a question in this generality. Okay, we discuss Hadamard manifold later. But in particular, any hyperbolic manifold of dimension 4 should be homotopy equivalent to some D alpha V simplicial complex, where D and alpha are constant.
And it is known that it has a fundamental group of 1?
Yes, so first a remark, X is contractible. Therefore, it means that pi n of M is 0, is trivial. The higher for all n which are bigger than 1. The fundamental group, the homotopy group are trivial except the first one. The fundamental group is the only one that is non-trivial. So in a sense, the manifold M is determined by its fundamental group. And if you recall, most originalities tell you that not only up to homotopy but also up to isometry. The manifold M is determined by its fundamental group. So in a sense, to bound the complexity of the manifold would be enough to bound the complexity of the fundamental group. So this conjecture is still wide open, except in dimension 3, where it's true because it says nothing. No, it's in dimension 3. In dimension, okay, I didn't define, but one version of this, I said that there are various versions of this conjecture. Another version is not to say that the dimension is not 3, but to restrict to arithmetic manifold, which I didn't define what it means. And then it still should be true. And then for dimension 3, it was actually proved by Mikolaj Frachik. So the conjecture is known only in dimension 3. But we'll discuss this later in the talk.
So the remark is for, I mean, the conjecture is only for when X is contractible? Or the remark is only...
No, a symmetric space of non-compact type is always contractible. It's always contractible. It's always diffeomorphic to Rn. So I will give example of symmetric space later, but you can show that it's always diffeomorphic to Rn. So they are all contractible, and therefore, in a sense, you only want to bound pi 1. And then this says that the following theorem is... so here is a theorem.
This is false for Hadamard manifold?
For Hadamard manifold, it's a question. So first, it is false for non-analytic Hadamard manifold, if the metric is non-analytic. But it should be true for negatively curved, even if it's non-analytic. And I think it should be true for non-positively curved if you assume analytic. But we will discuss it later. I don't want... In the Hadamard manifold, I'm less courageous, and I would call it a conjecture, but a question. But I will, yeah. Here I will be. I'm very, very confident that it should be true in the symmetric space. So here is a theorem. So. Let X be an irreducible symmetric space I hope that soon you will be comfortable with these notions. For now you can think of the hyperbolic space of non-compact type. Suppose that X is not H3. This is this assumption. But I also want to suppose that X is not SL3 R mod SO3. So I said that there is some five-dimensional symmetric space, which is a symmetric space of SL3, which is an interesting one. We will discuss it. But I want to assume that X is not that one.
It's of dimension 5?
Yeah, this one is of dimension 5.
Oh.
Because this group is 9-dimensional and this group is 3-dimensional. The symmetric space, this group is the isometry group of some 5-dimensional symmetric space. This group fixes a point. So, and this group acts transitively, so you can identify the symmetric space with this quotient. So it's actually a common thing to do in this theory, to write symmetric space. Sometimes I just write it G mod K, where G is a semi-simple link group and K is a compact subgroup. So this is many people just write G mod K, but they need a symmetric space. And so I assume I'm not this symmetric space. Then the conjecture is almost true in the sense that there are alpha and D such that any X manifold M is homotopy equivalent. No, sorry. Such that for any X manifold M, there is a D alpha volume M simplicial complex R such that I would like to say that R is homotopy equivalent to M, but I don't know to say that. But I do know to say that pi 1 of M, which is my group gamma, is the same as pi 1 of R.
And this is false for
Wait, so first, why I wrote gamma? Because I think of M as the X mod gamma, where gamma is a lattice, a discrete group in the isometry group G. And so I write it as gamma. And no, if it would fall, it should, the conjecture say that it's true for any symmetric space except this one. The conjecture is that it's true except this one. And much stronger is true, but I know to prove it under this channel. I have a proof that fails in this case. Yeah. The story is funny because when I started my PhD, first I realized how to do it for hyperbolic spaces in dimensional tree, and then I started to think about higher rank spaces. And I didn't know how to think about them, and then I met Alex Fuhrman, and he told me, well, maybe first consider the simplest case, which is SL3R, or SL2 times SL2. And today I know to prove it in all cases except SL3R, and if I assume irreducible, or if you don't assume it, so the other case I don't know is SL2 times SL2. so sometimes the simplest examples turn out to be the hardest case. So that's but let me have a break. But before the break, just say the two.
Can you say anything else about the other homotopy groups of the simplicial complex?
No, I don't know them. Yeah, I don't know them. We will see a proof of this theorem soon. But let's just first say the consequences. So corollary 1 is that is the following. So again, I'm a bit informal. So but let G be a simple, a non-compact simple Lie group. Suppose that G is not, and here I mean locally isometric. So I don't care about finite center. So a simple, okay, simple is no center. So it's not, suppose it's not PSL2C. SL2C is the isometry group of H3. And suppose that it's not SL3R. These are the two cases that I don't know to deal. Then there is a constant C such that for any gamma inside G discrete torsion free, pi 1 of gamma admits a presentation sigma R such that the number of relation is bounded by C times volume G mod gamma, and the number of generator and the number of relation is also, so I can write it actually like this, sigma R.
You mean gamma is
C gamma admits such a presentation, and all relation are at most, and all W in R are of length most.
What do you know about this if it's not torsion free, it's not true?
Okay, this is another theorem for later. If it's not torsion-free, I can bound a number of generators the same way. At the moment, I cannot bound a number of relations, but I think it's okay. Yeah, I can bound a number of generators. If it's not torsion-free, we will discuss it. I think I can say maybe also something about the number of relation. Maybe if I add a few more exceptions. Yeah. But later we will get to that. Yeah, all this theory is interesting also for non-torsion-free group, which amounts to study orbifold instead of manifold. Some of the questions are not more difficult, but some of them are much more difficult. So this is corollary 1. Corollary 2 is about counting, and then we go to a break. Again, like before, so under the same assumption, let G be a non-compact simple Lie group, and suppose the same assumption, so that G is not this. Then the number of gamma in G, which are discrete, let's say torsion-free, of volume at most V, up to conjugation. I don't want to distinguish. So this is bounded above by V to the constant. In any semi-simple Lie group, if you count lattices up to conjugation, you get this upper bound. So this is effective version of Wang theorem. And here I also need to assume that G is not SL2R. Because in SL2R, this is true, but we discussed type Miller theory. There are continuously many lattices which are isomorphic, but not conjugate. But so if you can do isomorphism, this is true also in SL2R. And here, for Itamar question, actually you can delete torsion-free. This I know to prove in all cases, even in SL3R, but not in SL2C because it's not true in SL2C. So this you can prove more generally. We will come back to it. So this is about counting. So as I said, this is another way to interpret the restriction coming from the volume on the complexity of the manifold. And this is, we mentioned last week that this is a question studied in number theory, like counting number field with bounded discriminant, or in asymptotic group theory, counting subgroup of bounded index in a given group, or counting finite groups. So this is related to this question. And so let's have a break now, and after the break I will tell you why the conjecture should be true. And like this will still be non-rigorous because okay, so let's have until 10 to 12 is enough.